everybody. Thanks for being here. Today we have the pleasure of having the speech of Carlo. So it would be great opportunity to see also another application of this technique. And we are very glad for giving us the opportunity to host this event. So, just a few moments about our meetup. So, our meetup was founded in February 2016. So, it's been quite a long journey together. So, in recent months, we have a lot of new people coming to our meetup, and we are glad to see that because the strength of this meetup is having the opportunity to be able to build a network of people with the same interests and sharing the same passions, the same use cases, so to be able to develop something better together. We recently passed the 2,000 milestone members, and we welcome today our 20 members of the last 3 weeks. These are the people that currently may make this possible, but as you know, if you participate in our past events, we want you to be part of our meetup. We want you to introduce yourself to us, to be able to provide some content for our community and some speech. So whenever you want, you can get in touch with us through our social networks. And we also have a huge repository of past events. You will find actually almost every speech of the past 7 years on our YouTube channel. So there you can find all the content that has been shown in the past meetups. We also have the account on SlideShare. So there you will actually see the slides that you can download to deep dive into the topics. And we also have a medium blog, so you can go there to see the contents of the past meetup as well. And these are the main channels in which we would like to get in touch with you, and we want to develop a community around, so LinkedIn and YouTube for all the content. So if you are interested in a talk, or if your company, you think that your company has something related to science application, so life science around this work, get in touch that we can, so that we can organize a talk together. So I will leave the floor to Vito for a small company presentation, and then for the subject.
Hello everybody, I will take much time for your presentation. Just we are my name is Claudio, I'm partner of Digital, and this is our and we build software solutions for companies, banks, and labs. And we're so happy to have all of you here today. We starting again recently to do events and meetups after COVID. So we are more and more interested in follow us. How are you
Okay. So hello everyone. I'm glad to be here today to give a talk for Data Science Milan, and in particular I'm going to talk about the NILM, which is a home energy disaggregation algorithm. So a little bit about myself. So I have some years of experience as data scientist, particularly in manufacturing industry 4.0, and also some experience with voice bots, which is basically voice assistants like Siri that we use every day. And at the moment I'm working on augmented reality, in particular for training of machine operators. So I'm developing an app, and this is my full-time project at the moment. So I decided to give this presentation because basically we are, as data scientists, usually deal with social and human-generated data. So if you think about social networks and analysis of user data for marketing or other applications, this is a common application of data analysis. But something that is interesting to me is the analysis of physical data, which most of the times follow physical rules, so they are more they follow more strict patterns compared to human data that is sometimes unpredictable. That is the reason why I decided to study more about this topic. As I said previously, the algorithm that I'm going to talk about is NILM, which is the acronym for Non-Intrusive Load Monitoring, which is basically, as you can see in the picture, you can see many home appliances, washing machine, a microwave, and a fridge. And what we want to do with these home appliances is basically understanding what is their energy electricity consumption at any point during the day. So the most simple approach to solve this is to install sensors. So individual sensors for each appliance, which like a watt meter that helps us solving our problem. But what is expensive, of course, we need to do installation and buy these sensors. But what we are trying to do is to just have one unique sensor that measures the energy consumption for the whole house, and then using machine learning separate the single signal for each of these appliances. And by the way, we know that each house has already installed a meter for measuring the electricity and for billing. So in this case, we wouldn't even need to do additional installations. As you can see, the algorithm with the one in the middle that converts the home aggregate energy consumption to the individual appliances and consumption. To give us an overview of what each single appliance is consuming. As I was saying earlier, this is physical data, which most of the times follows simple patterns, simple linear equations, and which wouldn't even need more advanced machine learning algorithms. But we can use machine learning to basically find out about these patterns without having to manually extract them. So in terms of why do we need to do this? So of course it's good to have as much data as we want for our house, and a nice app that tells us about the single appliances consumption. But that's not the only goal. Research has showed that having better awareness and feedback on single appliance consumption can help us save energy up to 15%. And of course, this can help us saving money, but also for environmental reasons, reducing emissions by saving the energy electricity consumption. So by looking at this problem, we can name it as blind signal separation. which is a common example of this problem in the cocktail party. So just picture, for example, that we are at a party and we're talking to someone, and there is background noise such as the music and other people speaking. So what our brain is able to do is to separate only the signal of the person, of the voice that we want to listen to. So this is like a parallel to what we are trying to do now. So instead of audio, we have current data, which is but it could be any kind of data for this problem. So just a review of what it is that we are trying to extract. So it's power, which is basically a product of current and voltage. So we have the time series data over the day or over the year of the consumption of overall consumption at each point in time. And so given this consumption, there are two problems that we can describe. The first is, which is more simple, just being able to tell whether, for example, the fridge is on or off at any given point in time, which is the on-off state. And the other problem that we can fix, which is a bit more ambitious, is trying to tell at each point of time what is the power consumption. So not just whether it's on or off, but also the load. So in order to find and model our algorithm, we basically we are not gathering data from scratch, but we are using existing datasets. By the way, this is not. I did it just for interest. It's not something that I do for my personal work. So I'm going to present some papers that I read about how researchers approach this problem. So they use mainly this dataset, which is the UK-DALE and the REFIT dataset, which are publicly available and free to download. So the first one gathers, they basically recorded the energy consumption for 5 houses in the UK, 6 seconds reading frequency between 2012 and 2015. And for the red dataset, it's 6 houses. In this case, it's 3 seconds frequency for appliance level and 1 second frequency for overall house level. And the appliances in this case, they are dishwasher, washing machine, microwave, fridge, and kettle for the UK-DALE. Okay, so here the approach that we follow in the training of the model is basically training on most of the houses and keeping one out for testing. And this is useful because we want the model to be able to generalize. So even if it's never seen a house before, it must be able to predict accurately and solve accurately the disaggregation problem. So this is what each of the papers is doing. So in terms of algorithm that has been tried, this is a problem that started to be studied in 1992 by George Hart, and many algorithms have been tried. So they started with KNN, SVM, the Markov model, and more recently they tried with neural network, which of course showed an improvement in the performance of the model. For example, one common approach is the sequence to sequence by Kelly and Nockenberg. So as you can see here, this is the sequence to sequence. So imagine that we have our time series of the house power consumption during a random day. So we are what they used to do previously, they were basically fitting the whole data set and considering the whole time series as an instance for training. But what they did here is they considered it as they just consider smaller sections of the data, which are like time windows that are sliding along the time series. So, for example, imagine that we're taking the time between 9 and 10, and then just that smaller section we're using it to do the prediction on the single appliance. Let me hide this so you can read also. Okay, so here there's the mains on the left, which is the overall, and the single appliance, which is our target. So this is a good approach we use to reduce the compute load, and then this slide the time window for one time step and do another prediction, for example 901 to 1001. Of course, this has been an improvement, but this approach gives a problem because, of course, for each single time step, we're doing multiple predictions. So at the end, we will have to take an average over each single prediction for each time step. And this turns out to show smoothen edges on a single curve. So for example, this could be a rectangle, but given the fact that we are taking averages, it's becoming it's showing smoothen edges. Another paper tried to fix this problem by predicting not the same time window given as input, but just a midpoint. So in this case, for example, we have the same time window as input, and as target we have the midpoint. So we're predicting each time step only once. And as before, we are going to roll along the time series. And of course, we need to add zero padding at the start and at the end of the time series in order to fit the whole sequence. And now let's look at the algorithm that this paper used for fitting the model. So what I used for the sequence to point is 5 layers of five convolutional layers, one dense layer, and then the output layer. In this case, you can see that there are two output layers, one for the sequence to sequence and one for the sequence to point. And this is because the authors of the paper, they wanted to compare the performance using the same architecture but for the two approaches. And they noticed that the sequence to point gave a better performance. So in terms of evaluation, they basically use mainly two metrics. One is the mean absolute error, one is the signal aggregate error. Basically, the mean absolute error is just for each prediction, computing the mean of the error across all the single time step predictions, which is a more difficult approach, more difficult metric because we must be precise at each individual point. While for the signal aggregate error, we are basically computing the error at the day level. So, and this helps because if there are some portions of the day where the prediction is not accurate, then it can be averaged over the whole day. So usually this tends to be an easier metric and give a lower error. So let's give a look at the results. You can see on the right the individual power consumption of appliances, and comparing it to the results from the paper, we can see that, of course, this is not yet a perfect problem that is perfectly solved, but it can already see some use cases. Using the sequencing point, we had 84% improvement of the NILM and 92% improvement on the SAE as compared to the sequence-to-sequence. Now we're going to look at another paper that tried to analyze this problem, which is basically they used an architecture that is very popular, that become very popular, which is the encoder-decoder with attention. And they basically reconsidered the problem and split it into two smaller problems. One is classification and one is regression. So as we said before, there are two things that we can do with the aggregate data of the menu, which is one predicting whether each single appliance is on or off at a given point, and one is predicting what's the power consumption at any given point. So they try to model a neural network that is parallelly solving both problems. So in order to train it on the on-off states, they had to preprocess dataset, and basically the dataset initially was just showing the power consumption. So they made it to show the on-off states by giving it a threshold, and so if it's below the threshold, it's off. It's above the threshold, it's on. The appliance, and so giving this pre-processed data, they used it to fit the classification problem. And then once they have the output of these two sub networks, they take a product of them to give the final output that is used for the evaluation. So here this is a quote from the paper. So they're using the attention model to basically understand which are the portions of the sequence where there is an activation. So when an appliance turns from on, becomes from off to on, and using attention, the attention mechanism. Basically, this helps improving the performance because these are crucial points in the sequence. So here you can see the architecture. On the left, we can see the stack of the regression, which is the autoencoder with some convolutional layer, SDM, the attention layer, and then dense layers for the decoder. And on the right, we have the classification network. And so the two initial inputs, as you can see, they are multiplied to get the final, the two initial outputs are multiplied to get the final output. So in terms of performance of this attention model, they demonstrated that it achieved better performance compared to any other approach, which is the last one. For example, as a reference, you can take a look at the sequence point. These are the metrics are the NAE, the SAD, and the response score. And you can see that all errors are lower, while the response score is better. You can also give a look here at the plots of the prediction versus actual. So the prediction is the blue curve, are the blue curves, and the orange is the the actual is blue curve, and the orange is the prediction. I highlighted the sequence to sequence on the left, while the attention architecture on the right. So you can see that the sequence to sequence. So in terms of colors, the blue is the fridge, and the green is the dishwasher. So you can take a look and see how the attention architecture is better and is able to follow more accurately what's the actual curve of the power consumption. If you want to try our hands on this problem, these datasets, as I mentioned earlier, they are open source. There is even a Python library called NILM, which allows us to simply load the datasets and convert them across different formats. So you can take a look at that if you're interested in playing around with it. And the format could be like a CSV with timestamps on the index column and individual appliances as the other columns. So I want to talk about what are some use cases of this algorithm. So we can imagine a simple app like this that can tell us our cost for each of our home appliances. For example, I put some random numbers in terms of price, but €6 per day for the washing machine, and then also give us the time by time over the day when we use this appliance. Imagine, for example, providing this information to the cloud, where there is an NILM algorithm that is running, and then sending back the analyzed information. So as I said earlier, we can, according to research, having a feedback better feedback on the appliance consumption can help us saving and reducing our and improving our habits in terms of energy consumption up to 5-15%. And of course, this is not perfect yet. We have seen that there is still some margin of improvement, but we can also look at it for more simple problems. Imagine that we are looking at the power consumption to tell whether to say whether there are some people inside our home. For example, if there are people switching lights on and off. So this is a signal that there's someone inside. And this could be used, for example, for a home automation technique. For example, for turning acting on the thermostat and saving on heating when nobody's there. So in terms of drawbacks, we could look at the privacy. This is we can think of our power consumption, our mains as very sensitive information because we can extract a lot of data from it once these techniques will improve. For example, we can say what are the habits of people when they're around, what they're using, and so on. So this is something to keep in mind. And of course, the NILM is not the only application of electricity analysis, but the current signature could be analyzed also for other purposes. Let's think about industrial machinery and how we can use the current signature to predict possible failures of machines, which is something called predictive maintenance, and it's done with other approaches such as vibrational sensors. But current could be also a possible alternative. And of course, we can analyze current to be able to predict future consumption, which is useful in the context of smart grids and demand response, which is basically when we need to balance what's the supply and the demand of energy inside the grid in order not to overload it, which is something that could be dangerous for the grid. Yeah, these are the final considerations on the topic, and thanks a lot for listening and being here. And there's a link, a QR code where you can check the LinkedIn page for my work on augmented reality, and yeah, so feel free to check it out. Thank you. Any question?
I have one. For the final consumer, what it will implement? I mean, does it provide some techniques to the new inside his house in order to measure all the consumption of the household appliances?
Yeah, so currently every house already has a smart meter, which is provided by the utility company and is used for analyzing how much energy we're consuming and how much we have to pay every month. But sometimes the frequency for that is like every 15 minutes, so it may not be enough for this kind. I mean, potentially it could be used if we had access to higher frequency data, but what we can usually access is just a 15 minutes interval, so it may not be enough for these purposes. In which case we will have to install an additional watt meter on the incoming grid line. I don't know. Yeah, quite similar. Yeah, it's a simple watt meter. Yeah, it's very common. Sensor.
I think you can buy it for like 13
Oh,
put it per meter.
okay.
And if you want the frequency to some sort of 15 minutes, maybe they already have a line.
It's not something complicated.
But you have to buy each for each account.
Okay. But here we said that it would be
Yes, for
one
this, one for all.
Yeah.
Another question. Can we go back to the slide where you presented some of the graphs? I'm not sure of the number.
That's here.
That's great. So I was trying to understand the graphs. In the prediction on the left, you're saying it's the sequence to point
Yeah, this
model, right?
This one.
You're highlighting the fridge and the dishwasher.
Yeah, that's right.
And this is every 15 minutes.
No, the frequency for this is, as I said before, is around 1 per second. Or could be less.
And the results, I mean, I'm just curious about your opinion on these types of results, because we can see the MAE, or the SAE, but then at the end of the day, I think what matters is trying to understand these graphs here, because the error, I mean, if you consider the sum of the energy consumed in one day, these appliances most of the time are zero, right? Sometimes most of the time are off. If you think of, I don't know, the dishwasher, it's different for the fridge, because the fridge is like every 15 minutes it cycles up and down. But I was impressed by that graph on the right side, which is kind of exactly the same. But only the baseline is a little higher. I can't really see the graph, but I guess my question for you is, what do you think of these results? Forget about the numbers of the 7 blocks or the what's your point? What's your opinion?
Yeah, I mean, these are just the sum of the graphs, of course. They don't represent everything. It could be that these are like good results, but it could be like worse curves. Of course, they are not 100% reliable. As you can see, yeah, as you said, on the right, the blue line is above zero, the ground truth, but the prediction is on zero. So I think depends on what we need this prediction for. Like it will not be used, of course, for metering, because we will be paid more. We have to pay more than what we're actually consuming, or less. But if we use it for other applications, like as we were saying, occupancy detection, or just for personal consumption, so we don't need something that is 100% reliable. Yeah, I think it depends on the application.
Do work with different manufacturers, right? So I'm guessing my point is, do you think we are at a state where we are mature enough to use this for applications that are not personal? Your opinion is just a call.
Yeah, I haven't personally used this for work, but I think depends on what you use it for. So yeah, for example, you can use it for a machine, as I was saying, to predict whether it's going to fail or it's going to break down soon, so that we can fix it and avoid downtimes. That could be one possible application. So we use like this algorithm to break down individual components, and then we use those individual components as inputs for some other problems, some other yeah, problems that we want to solve. Okay.
I have a couple of questions. First one is in the sequence-to-sequence model. I know it's not the most performant one. Just to understand what was the architecture. So my understanding is that like ChatGPT is a sequence-to-sequence. So you first feed in an input that's a series, and then at the end of this, that's the encoding part. Then the decoding part starts, and then it's trying to generate the output is a series.
Right.
So also for them, the process was you have an input at the end of the input. That's the main, and then that model was trying to regenerate the original series of that specific appliance, or it was more like a recurrent neural network, and every step you also have an output on top of it.
So the sequence to sequence doesn't use the encoder decoder. You're talking about the one using encoder decoder.
No, I'm sorry, but forget about this word. So the idea is that you feed in the input, the input finishes, and then it starts trying to regenerate the output afterwards. It's not happening in real time, right?
Yeah, it's all done first to the decoder, and then step by step the decoder regenerates.
Another question. So probably they have not tried. Just see what you think. So are all these houses they're using having the whole set of appliances? In the sense that what happens, because you also have the raw signals of everyone. What happens if you filter out, for example, the fridge? Let's see, there's an house that for any reason doesn't have a fridge or doesn't have a dishwasher. In the end, let's say an house that doesn't have the dishwasher. The model that tries to detect the fridge, is the performance the same, or is somehow dependent on the fact that the original ensemble of signal is a mixture of signal from the same set of appliances?
Yeah, actually, I didn't probably I didn't explain the I wouldn't emphasize on that, but they're modeling a network for each appliance. So, for example, there were six appliances. So they model a different network for each of them. So there is one that extracts the fridge, one that extracts the washing machine. So in that case, yeah, I don't know at that point whether like the aggregate appliances matter or I mean they are doing anyway transfer learning between different houses, which I mean those all houses in the training and testing they are the same around the same appliances.
Yeah, because there would be interesting to see whether the model generalized to extreme scenario, because more or less all the house for the targets are the same appliance. But it would be interesting to see what happens if for any reason there's a house doesn't have a fridge. Is the dishwasher model performance kind of dropping because it's also expecting?
Yeah, that could be actually. Yeah, I think they all are the same, so they didn't talk about like some houses that were missing one. No questions? Okay, then thanks again. I think we're going for the aperitivo. So.